Today's lesson is 4-6, multiplying and dividing monomials. We're going to talk about some rules and some tricks when we're multiplying like bases or dividing like bases and seeing what happens to those exponents. See if we can learn a few shortcuts. Alright, let's go ahead and jump in. Recall that exponents are used to show repeated multiplication. We can use the definition of exponents to help find a rule for multiplying powers with the same base. We'll start out with an example. If, for example, we were asked to find 2 cubed times 2 to the 4th, we'll start out with what 2 cubed means. What does this mean? This means 3 2's multiplied together. Okay, so there's 2 cubed, and I'm going to multiply this by 2 to the 4th. Well, what's 2 to the 4th? 2 to the 4th is 4 2's multiplied together. There they all are. So what I've got in total is I've got 1, 2, 3, 4, 5, 6, 7 2's all multiplied together. Well, I could simplify that using an exponent and say that is 2 raised to the power of 7, because 3 2's multiplied together times 4 more 2's multiplied together give me a total of 7 2's multiplied together. Notice this works because I'm multiplying like bases. The bases are the same. That's what like bases mean. So if I am multiplying like bases, what I can do is, it looks like, what can I do with the exponents as a quicker way to do this? Well, it looks like we just added the exponents. In fact, there's our rule. When multiplying powers with like bases, we can add the exponents. So if I had a to the power m times a to the power n, I'm multiplying powers, bases with exponents, and the bases are the same. In this case, they're both a. I can simply add the exponent. So it is that like base raised to the power of the sum of these exponents. Okay, it doesn't get much more general than that. It gets more specific when we start using these numbers. But notice the base stays the same because now I have this many a's multiplied together, because this says I have m a's multiplied together and n more a's multiplied together. So when I put all of that into one basket, I end up with m plus n, however many that is, a's multiplied together. So, for example, if we were asked to find 7 cubed times 7, we could follow the rule and say, well, I'm multiplying powers. This exponent, I don't see it because I assume there's 7. So I can use my rule and say, oh, I'm multiplying powers like bases. The base is both 7. So the solution to that would be 7 raised to the power of 3 plus 1, which would equal 7 to the 4th. Now we can always go back and check this. This is what I like about a lot of these rules. They're shortcuts, but if you're not really sure of them, you don't have to take the shortcut. You can always verify if that's what you're into. So what this means is I have 3 7's multiplied together times, that's this guy right here, times 1 more 7. So that says, hey, I'm multiplying 7's together repeatedly. How many 7's am I multiplying together repeatedly? 4 of them. So I don't always have to use this rule, and that's what's great about math. If I don't recognize it, which is, in my opinion, the hardest part about algebra, is recognizing what it is you're looking at. If I don't recognize this as multiplying powers with like bases, that's okay. I can always use the definition of exponents that we know and still come up with the exact same answer. Okay, what about a slightly more challenging example? What if we were asked to find, how about, ooh, there's a good one, x to the 5th times x squared. What's x? Well, I don't know. Good news is it doesn't matter what x is, because the rules still apply. I'm multiplying powers and they have like bases. The base is both x, so I can use my rule if I remembered, if I recognize this, and say, oh, that's the base raised to the power of, add the exponents, 5 plus 2, so that's 7 x's multiplied together. Again, you can always check by saying, oh, well, this is 5 x's, 3, 4, 5, times 2 more x's multiplied together, And when all is said and done, that's just repeated multiplication of the base x, and that's 7 of them multiplied together, so I get the same solution. Okay, how about an even more challenging problem? Okay, this one's slightly more challenging because there's a whole lot of stuff going on here. Here's what I need you to recognize first and foremost, is that these things, parentheses bumped up against each other, imply multiplication. And what I'm multiplying is this chunk of information times this chunk of information. So both of these are monomials. Yes, there's a negative sign there, but it is associated with this term. There's no adding or subtracting going on here. So this is one term, this is one term. So it's important that I recognize that I'm multiplying these two things and they're both monomials. That's important. Okay, if there were two terms in these parentheses, it'd be a different story. But since there's not, we can multiply these. Now, we're going to use a couple of tricks, pull a couple of tricks out of our toolbox, and say, well, I can multiply in any order I want. There's a property that says so, and that property is, yeah, you got it, the commutative property. So what I can do is I can multiply these in any order I want. What I'm going to do is I'm going to break some of these up, and I'm going to break -4 times n cubed times 2 times n to the 6th. And I'm going to rearrange these because it's all multiplication. I can multiply in any order I want. Notice I kept the negative with the 4, okay, because that coefficient of n cubed is -4. What I can do is I can multiply in this order. Okay, well, what's beneficial to that is I can multiply -4 and 2 together. Okay, that's 4 times 2, which is 8, and a negative times a positive gives me a negative. Or I have two -4s, which is -8, another way to look at it, times n cubed times n to the 6th. Well, I can recognize this as taking, or powers, multiplying powers with like bases. Both the bases are n, so I can add the exponents. That's n to the 3 plus 6, and then I can clean this up and say that's -8 times n to the 9th. Not so bad, a little challenging, but I'm pretty sure you can handle it. Okay, let's move on to the next topic, which is dividing monomials. It turns out there is also a rule for dividing monomials or powers with like bases. The base is still 2 here. Let's see if we can discover that. We'll do that by trying this question: 2 to the 6th divided by 2, or 2 to the 1st, because 2 is just one factor of 2. 2 to the 6th is 6 factors of 2. 6 2's multiplied together. So I'm going to expand these out. What is 2 to the 6th? Okay, well, that's 6 2's, 1 2 3 4 5 6 multiplied together, divided by one factor of 2. And we went over and talked about, not too long ago, that anything over itself equals 1. So this 2 over 2 is equal to a factor of 1, which gives me, when I simplify this, okay, these are going to become a factor of 1, which leaves me with 1 2 3 4 5 2's multiplied together. So I'll write that as 2 to the 5th. Okay, so can you come up with a rule when you're dividing powers with like bases? What happens to the exponents? You got it. When dividing powers with like bases, again, very important that the bases are the same, we can subtract the exponents. So our very general example, if we have a to the power m divided by a to the power n, that's going to equal my base a raised to the power of m minus n. Or a numerical example, 4 to the 5th divided by 4 squared is the same as 4 to the 5 minus 2, which is 4 cubed. Now again, if you're not really certain about this, you can expand these out. 4 to the 5th is 5 fours, 3, 4, 5 fours multiplied together, divided by 2 factors of 4, and anything over itself, there's a factor of 1, there's a factor of 1, so I'm left with 3 factors of 4 multiplied together, which is 4 cubed. So using this new rule, let's see if we can find the quotient of 5 to the 7th divided by 5 to the 4th. Well, using our rule, if we recognize this as dividing powers with like bases, in this case they're both bases of 5, then I can just apply my rule that I would subtract the exponents. So that's 5 raised to the power of 7 minus 4, which is 5 to the power 3. Take the time to write this out. Do yourself a favor. If you don't recognize this as dividing powers with like bases, well, you can always say, well, I'm going to see what this equals. That's 7 5s multiplied together. One, 2, 3, 4, 5, 6, 7. There they are. Divided by 4 factors of 5 multiplied together. And it's really hard to say 4 and write 5, just so you know. And this 5 over 5 equals 1, this 5 over 5 is a factor of 1, and so on and so forth. So I'm left with 3 factors of 5 multiplied together times 1, which doesn't change it. So I end up with 5 cubed. So even if you don't recognize this rule, okay, sure, it'll save you a little bit of time writing it out, but not much. Okay, if you are one of those people that likes to memorize rules, that's great. But what's really important is you have to make sure that the rule is allowed to apply. And when you're dealing with exponents and powers and applying these rules, what's of utmost importance is that these bases are the same. Okay, if these bases were not the same, you can't just say, hey, I'm dividing, so I'll just subtract fractions. You have to make sure the conditions are right for you to be able to do that. Let's try one more example. Alright, so y to the 5th divided by y cubed. If you recognize this as an instance where you can say, I'm dividing powers with like bases because both of these bases are y, then you can say, hey, I remember that rule. When I'm dividing powers with like bases, the result is going to be that base to the difference of the exponents, which would in this case be 5 minus 3, which would be y squared. Or if you're one of those people, like me sometimes, who may not recognize this, and you're asked to divide that. Well, geez, dividing, I know what that is, but let's see if I can do this. Y to the 5th is 5 y's multiplied together, divided by 3 y's multiplied together, and every y over y equals a factor of 1. So what I'm left with is 2 factors of y's multiplied together, y squared. Oh, hey, that's the same as this. Notice, once you get the hang of this, this doesn't take a whole lot longer than the rule. Okay, so, and I'd be, again, kind of careful if I were you, trying to just apply the rule every time, because you have to make sure the rule fits. Okay, that's it for now. We'll see you next time.
If I